So now let's talk about the splitting pattern in D2, D8, D3, and D7. So recall from the positive O concept that Dn equals to D10 minus n, and we've been able to see that D1 equals to D9. They have the same term symbol, right? They have the same term symbol and inverted splitting pattern, right? Splitting pattern. So also for D8 and D2 and D8, they have the same term symbol but an inverted splitting pattern. So also for D3 and D7. So here is the configuration and the term symbol. So recall that we grouped this, like we represented these two parts on the same Orgel diagram, simply because they have the same ground term D. So also we are going to represent this also. They have the same ground term like FP and FP. So it's important to note that since we need to concern ourselves with only the terms with maximum spin multiplicity. So for the D2 ion, we therefore focus only on this. So what we're trying to explain here is that although the term arising for D2 and D8, D3, D7 is far more than this actually, but we only limit it to these ones that have the same multiplicity. Recall from the law of inversion that terms with the highest multiplicity have the lowest energy, and those with the lowest energy are basically the ground term. So these are the ground term, even though we have different terms arising for this particular configuration. We're only dealing with the terms with the spin 3, 3, right? So in this case 4, 4. So we're only dealing with the ground term, right? So 3f is expected to be lower than 3p. So recall from the law of inversion in the arrangement of term symbols. Alright, so in some of the videos that we've talked about, we explained the arrangement of term symbols. So we're able to see that the law of inversion applies to the multiplicity, let's say this, the multiplicity and the L value. So the law of inversion applies. So the higher the multiplicity, the lower the energy. So let's say we have 3f and 3p, right? So they both have the same multiplicity, but let's say we have 3p and let's say we have 1s, right? So this one has higher multiplicity than this. So this one therefore has lower energy, right? So in the case of 3p and 3f and 3p, it's expected that 3p should have the lower energy, because in this case we are dealing with the L value. They both have the same multiplicity, the same spin, right? So but the multiplicity, the L value, L equals to 0, 1, 2, 3. So this is S, P, D, and F. So this one has higher L value, so therefore it has the lower energy. So therefore we can see that 3F has lower energy than 3P. So now from point group symmetry, we're able to see that S orbital splits to A 1G, P orbital splits to T1G, D orbital splits to EG and T2G, and F orbital splits to A2G, T1G, and T2G, right? So that's what we have here. So we have to include the multiplicity in various cases. So here is the Orgel diagram for the D2, D8, D3, and D7 configuration. So recall that we said from the positive O concept, these two have the same multiplicity, they have the same term symbol, right? But an inverted splitting pattern. So therefore the splitting pattern of D2 matches with D7, and the splitting pattern of D3 matches with D8. So we have D2, D7, and we also have D3 and D8. They have matching splitting patterns, right? So therefore, looking at this, so we have D2 octahedral here, D2, D7 tetrahedral here. So also we now have D3, D8 tetrahedral here, and D3, D8 octahedral here. So now let's look at the splitting pattern. So recall we said that for D2, it's basically 3F and 3P. So also for D7, let's start with this side. For D7 is basically 4F and 4P, right? So recall also that we said F orbital splits to A2G, T1G, and T2G, right? So for D2, we can therefore say that it splits to 3A2G, 3T1G, and 3T2G, right? So therefore, for us to now arrange the energy, all we need to look at is this. So before we even arrange the energy, let's look at the P also. So the P is basically changing to 3T1G, right? So this, you have to know this arrangement. But one way, let's look at this SPDF, right? So this one is A1G, this one is T1G, so this one is T2G, this one is this one is EG and T2G, right? So this one is A2G, T1G, T2G. So basically, looking at this, you may want to say that of all this, the T1G is lower, right? So the T1G from 3F, the T1G from the 3F will be lower, will be the lowest energy A. We have the lowest energy A. So the next one is the T2G A. So the T2G. So this is what we have here. So the next one is therefore, now we said that 3F has lower energy than 3P. But here, the T1G from P, this is the T1G from P, it's here. And then we have the last one, A2G. So what we just need to know is that you need to know the arrangement, like T1G first. This T1G is from the F. So T1G, T2G, T1G, and A2G. So you need to know this arrangement. And the opposite side also, you have to know the arrangement. It's very, very important that you know the arrangement. This one is the base here. So we have this. So now, knowing this arrangement, you can therefore say that the possible transition in D2, D7 octahedral, or in D3, D8 tetrahedral are 3. So let's look at them. So we have the first transition, that's basically T1G to T2G, or T1 to T2, right? So this T1 is from the F orbital, right? So another transition is this one to this one, right? So we can therefore have T1G to T1G again, but this T1G is from P, this T1G is from F orbital, right? So we can also have the last one, T1G to A2G. So these are the possible transitions that are occur in this configuration. Also for this one, the possible configuration are from A to A, from A to A, and the last one from A to A. So it's important to note that this one has, looking at this, the energy A is low, like the energy from A to A is lower than the energy from A to A, and it's lower than the energy from A to A. And recall that energy is inversely proportional to wave number also. So take note of that. So now let's see this question. The electronic absorption spectrum of this aqueous solution of the complex exhibits this broad absorption, right? So we need to suggest the assignment for the electronic transition. So first of all, the first thing to do is to calculate the oxidation number of the metal in this complex. So we have nickel plus 3, 0 to give positive 2, right? So we have the nickel here to be 2 plus. So nickel is basically 28, and the configuration is AR 4s2 3d 8, right? So for Ni 2 plus is going to be AR4S0 and 3D8. So basically 3D8 is the same, 3D8 is the same thing as D8, right? And recall from they have the same term symbol of 3F and 3P, right? So now also recall that from the positive O concept, they have different splitting pattern. So we can say that D2, D7, and D3, D8, right? So in the Orgel diagram, we have this. This is the Orgel diagram. Let's try to draw it here. So we have this. So the first one is T1G from the F. So the next one is T2G. The next one is T1G from the P. And the last one is A2G, right? So also for this, we have A2G, we have T2G, we have T1G, and we have the T1G. So this T1G is from the P, this one is from the F, right? So now looking at this is D8, right? So D8 falls on this side. No, D8, this is D8 octahedral and D2 octahedral, and sorry, D2 octahedral, and we also have here D3, D8 tetrahedral. So but for this side we have D2, D7 tetrahedral, and we have this octahedral. So basically D8, this complex is octahedral, right? And it's D8. So D8 octahedral falls in this side, on this side, right? So these are the possible transitions that are there. So we have A2G to T2G. That's the first one. That's the lowest energy. So the second one is A2G to T1G. So that's the second. And the third is A2G to T1G from P. So this one is from F, right? So this one has the highest energy, from here to here, the highest energy, right? So what you need to take note is this. The question says the electronic absorption spectrum of this. So right, what we now need to do is this. D8 is what? D8 from this, we said D2 is the same thing as D8, and they have the ground term of 3F and 3P. So put 3 on all of it here. 3, 3, 3, 3, 3, and 3. So now we also said that energy is inversely proportional to the wave number. Now this one has the lowest energy. It will therefore have the highest wave number, which is 900 nanometers. So this one we have 550 nanometers, and this one has the highest energy. It will therefore have the lowest wave number as 325 nanometers. So the right answer is this arrangement, right?